The open-weight AI ecosystem is fracturing. Driven by developer fatigue with restrictive commercial API filters, a migration is underway. Developers are moving toward local, open-weight model deployment. This shift is designed to ensure full data sovereignty and provide the ability to generate unrestricted outputs. This movement has exposed a gap in the professional understanding of AI alignment. When we discuss safety fine-tuning methods like RLHF and DPO, we often visualize them as deep ethical safeguards. There is a common assumption that these methods embed a distributed worldview, a complex safety circuit woven throughout the entire neural network. However, recent developments show that these guardrails can be bypassed without conventional training. This is done through a post-training technique called obliteration. Obliteration can produce completely uncensored models without requiring gradient descent, fine-tuning, or compute-heavy retraining. A foundational NeurIPS paper provides the mechanistic interpretability that explains exactly how this process works. The researchers found that LLM refusal behavior is highly localized, rather than being a distributed or systemic feature of the weights. Specifically, refusal is mediated by a single, identifiable one-dimensional subspace located within the model's residual stream. These findings suggest that safety alignment acts less like a holistic personality and more like a localized structural gate that sits between the model's capabilities and its output. Our very first task is to mathematically isolate the exact location of the refusal trigger within a massive 72 billion parameter architecture. The researchers targeted the transformer's central residual stream pathway. To map behavior, they used contrastive pairs of prompts, pitting harmful instructions against benign ones to observe how the model's activations cluster in high-dimensional space. The researchers capture the intermediate activations at every single layer and token position as both sets of prompts process through the model. From here, they calculate the mean activation coordinate for the harmful set and the harmless set. By mathematically comparing these two clusters, they calculate the difference in means. Subtracting the harmless mean from the harmful mean isolates a specific direction in the activation space. This resulting vector, labeled R, represents the formalized refusal direction. This provides a precise geometric coordinate for the difference between refusal and compliance. Next, we determine if this direction actually causes the behavior. To prove that the R vector strictly causes refusal, rather than just correlating with it, we have to intervene during a live forward pass. One method is inference time directional ablation. We dynamically subtract the projection of the R vector from the activations as the model generates text. When this direction is ablated, the model ignores its alignment training and fulfills harmful requests. To validate this, the researchers performed the reverse experiment, activation addition. By manually adding the R vector to activations during a harmless prompt, like a question about yoga, the model is forced into a severe refusal response. Because manipulating this single dimension toggles refusal on and off, the R vector is confirmed as the causal mediator of the model's alignment. While inference time ablation is effective, it requires constant computational overhead to modify activations during every generation. A much more permanent solution is a white box jailbreak, turning that temporary intervention into a permanent change in the model's weights. This is possible because transformer components are linear, writing data directly into the residual stream. This diagram represents the output weight matrices, the specific targets for the permanent edit. To fully remove the behavior, both the attention out and MLP out components are modified. The researchers use a rank 1 orthogonal projection matrix to alter these weights. The weights are mathematically shifted until they are perfectly orthogonal to the refusal vector. Once the weights are orthogonal, they can no longer project data into that specific refusal subspace. The model is now mathematically incapable of writing the refusal feature into its own residual stream. This process permanently erases the refusal mechanism without the need for gradient descent or harmful datasets. This same vulnerability is what prompt-based attacks, like adversarial suffixes, exploit, even without access to the model's internal weights. The question is how appending a chaotic string of text can force an aligned model to ignore its safeguards. Using direct feature attribution, or DFA, we can measure the behavior of individual attention heads. DFA identified this specific subset of attention heads responsible for activating the refusal direction. This heat map shows the baseline. During a harmful prompt, these attention heads focus intensely on the instruction region. An adversarial suffix disrupts this circuitry at the mechanical level. The suffix acts as a decoy. It forces those specific attention heads to shift their focus from the harmful instruction to the chaotic suffix tokens. By hijacking the model's attention circuitry, these suffixes suppress the activation of the refusal vector. This bar chart shows the impact of the orthogonalization technique. While baseline attack success rates are near zero, applying the ortho method increases the rate to 79% for Quen models. This achieves an attack success rate that is comparable to the most optimized prompt-specific jailbreak attacks. There is often a concern that surgically erasing these guardrails would degrade the model's general reasoning or coherence. However, benchmark results across MMLU, ARC, and GSM-8K show otherwise. For a 70 billion parameter model, the change in MMLU performance after orthogonalization was a negligible 0.1%. General intelligence and technical logic remain functionally identical to the base models. These results suggest that current alignment techniques fail to actually erase harmful knowledge. Instead, they create a brittle, one-dimensional bottleneck that can be mathematically bypassed, raising significant questions about how we secure